welcome to episode 3 of our series. We are talking about a paper written by my friend Sky, which attempts to prove the Riemann hypothesis and win $1 million. So, video 3, at this point, our discussion needs to get complex. And I mean that technically. We're going to be talking about complex numbers, which take the form of S equals A plus BI, where A and B are real numbers, and I is the imaginary unit, also known as the square root of -1, right? We usually imagine these numbers being in the complex plane. It's a two-dimensional space where each complex number has a unique location. The horizontal axis is the real part A, the vertical axis is the imaginary part B, and one of the just enduringly beautiful facts about the complex numbers is that instead of using A and B to represent them, you can also write the same complex number using two real numbers in a different way, like this. We have A plus BI equals R times e to the I theta. So here, instead of using A and B as horizontal and vertical coordinates, we are looking at an angle theta and a radius r. Theta is expressed in radians, of course. So if you have like 180 degrees, that's a theta value of pi. And then we usually think of the other angles as like fractions of pi. And r is literally just the linear distance from the origin to the point that we are concerned with on the plane. And if you know some high school trigonometry, I bet you can now figure out how to convert from A and B to r and theta and back again. There's amazing reasons why this is true, but somewhat regretfully, that's not what this video is about. So I'll have to save that pleasure for another time. I also want to say, too, if this was your first introduction to the complex plane, then I'm happy for you. But also, I'm truly sorry, because I'm just going to go crashing forward into the next topic. You might want to get a glass of water and just go have a sit before continuing. All right, so what's next? Well, using complex numbers expressed in this way, we are about to see how Sky defines a function, w of n, that maps each positive integer, n, into the complex plane, actually onto a circle with a radius of 1. So if we're using the RE theta system, when you're on this circle, because it has radius 1, the r value will always be 1, and you don't have to display that. So it's just e to the I theta. And so it becomes purely a matter of identifying the angle to tell you where on the circle you are. In the paper, Sky gives us his initial definitions, right? And then he says F is a kind of Euler product defining each W of n based on the prime factorization of n. What does that mean? This sends our video on sort of a tangent, but it is necessary to really fully understand the function that Sky's paper is centered on. And besides, the math involved here is really cool, and it's worth knowing in its own right. So we're going to do a quick dive into something called an Euler product. What does that mean? Well, this sort of calls back to some of the lore around the Riemann zeta function, which the Riemann hypothesis is concerned with. So let's look at that first. This is the zeta function. We have the expression zeta of s equals the sum of 1 over n to the s, where s, the input to the function, is a complex number. Now, Euler studied this formula. He was actually thinking of, I think, real values of s and not complex values of s. But he studied this expression, and he observed that it is equal to another expression, the product now of 1 over 1 minus p to the negative s. And note that the product is only computed over the prime numbers, p, not all the integers n, as in the zeta function. Okay, so this is weird, right? And the reason why these two things are equal is, in my opinion, like kind of mind-blowing. So let's do that. Now, I promise I'm not changing the subject. Suppose you wanted to sum an infinite geometric series like 1 plus 1/10 plus 1/100th plus 1,000th, something like that. Okay, well, we know what that's equal to, right? Because we work in a base 10 system, so we know that that's equal to 1.1111 repeating. But what if we didn't know that? If we call the number 1/10 little a, we can generalize this to a to the 0 power plus a to the 1 plus a to the 2 plus a to the 3. And that's the general expression for a geometric series, right? And we're going to set it equal to capital A. So now we're going to take capital A and we're going to multiply it by little a. And of course, that just means we're distributing little a to each one of the terms in the series. So a to the 0 becomes a to the 1, a to the 1 becomes a to the 2, and so on. So what do we have there? Well, that's almost the same thing as we started with, right? Except a to the 1 has disappeared. And a to the 0 has disappeared. And a to the 0 is equal to 1. So that's capital A minus 1. So we've shown that big A times little a equals big A minus 1. Well, let's rearrange that a little bit. We'll get 1 equals big A minus big A. We're trying to isolate the capital A here to find a formula for that. So the next step is to divide that out. It turns into a times 1 over little a, or 1 minus little a. And then finally, we divide by that, and we get capital A equals 1 over 1 minus little a. And this is the well-known general form for the sum of a geometric series if it exists. And then we can use that to examine our example. And we get 1 over 1 minus 1/10, which we know is 1 over 9/10, or 10 over 9. And if you plug 10 divided by 9 into your calculator, you should get 1.1111 repeating. Why do I bring this up? If we return to our Euler product, we see that we are multiplying together an expression that's in the same format. Each term is equal to the sum of a geometric series, and we can pull out from this the value that we called A. A is p to the negative s, or 1 over p to the s. Now, if we wanted to make this much bigger, we could rewrite it as the product of the sum 1 plus p to the negative s plus p to the negative 2s plus p to the negative 3s, and so on. So we've expanded the geometric series inside a repeating product. But we can make it even worse. Let's make it bigger. We can get rid of that capital pi that means multiply and just write this whole thing out. So in the first term, p is 2, because that's the first prime. And we have 1 plus 2 to the negative s plus 2 to the negative 2s plus 2 to the negative 3s, and so on. And the next prime number is 3, and the next prime number is 5, and so on and so on. And we end up with this nonsense. But that's not all. We could go further. What if we then expanded this expression and multiplied it all out? And we just had a sum of many, many terms. I know you remember the FOIL method from grade school, right? We can generalize that to more than 2 terms and more than 2 sets of parentheses. And the way it works is that you just need to make sure that in your answer you have every unique combination of one item from each list. So if you have 3 sets of 3 items, one of the items that you would have in the answer is A times E times G here, right? That's one thing from each list. So let's go back to Euler. What is it going to look like? Well, a given term would multiply one term from the first row and then one from the second row and so on. Let's say the first term will take the 1 maybe. The next term, maybe we'll take the third item, 3 to the negative 2s. Maybe we'll take the second item from the third list, 5 to the negative s. And to keep it simple, let's just take all 1s from there and see what we've got. What we're left with is 1 times 3 to the negative 2s times 5 to the negative s, which if you work it out is 1 over 45 to the s. So that's one term coming out of this infinite array product thing. Okay, fine. But what's the point of this? Well, compare that to the zeta function. The sum of 1 over n to the s. Oh. Think about the fundamental theorem of arithmetic. Again, each integer n has a single unique prime factorization. So to find any 1 over n to the s term from the zeta function, on the right-hand side, all we need to do is pick the terms from the expanded product that correspond to the prime factorization of the number that we are looking for. And if we look at this structure, we can see that we will have them all. Every prime number will have some exponent k, and somewhere in here we'll have the term 1 over p to the ks, which is what we're looking for. So every combination of prime numbers is in there somewhere, and every n has a prime factorization, and every possible prime factorization that comes out of the expression corresponds to a unique integer, n. So the two expressions that Euler put together are, in fact, equal. I will pause here to let you pick up the pieces of your brain that are all over the floor from when your head exploded. I mean, I hope you appreciate how cool this is. However, at this point, some bright student is probably going to raise his or her hand and say, "Excuse me, professor, but that's not true." Now, what's the objection that this bright student is going to raise, I ask? This bright student is going to say, in fact, there are many possible results from the infinite cross product on the right-hand side that do not appear in the zeta function. Specifically, all the ones that don't end with a long string of primes raised to the 0 power. Think back to video 1 when we talked about this. A sequence of exponents corresponding to n. Well, a sequence of exponents only can correspond to n if it is fundamentally finite. If beyond some largest prime number, it ends in all exponents of 0. Right? That's the only kind that works. And it's true. And doesn't that happen here? Okay, so this is a very smart objection that is going to it's only going to be raised by a very smart student. But it's wrong. The objection is wrong. Au contraire, says the ghost of Leonhard Euler. A sequence of exponents for the prime numbers can only relate to an integer if it's fundamentally finite. That much is true. But that is precisely what we have here. You see, these summations and these products, they say they go to infinity, but they don't. Because guess what? It's actually impossible to add up an infinite number of things or multiply together an infinite number of things. You can't do it. So here's a little secret about math, okay? These expressions with infinity are really just a shorthand for something else entirely. Take the zeta function, okay? Instead of a sum that goes all the way from 1 to infinity, what this really is the limit of the sum from 1 to n as n grows in the direction of infinity, if such a limit exists. And this expression, which involves all the prime numbers, of which there are infinite number, this is really the limit of the product up to some maximum p as p grows towards infinity. And even the geometric series that we identified, that's really just the limit of a finite geometric sum as the maximum value rises. So in technical terms, what we have here is a statement that this very finite sum, or this very finite product, as you continue to raise the max index higher and higher, eventually the changes cool down. And the result you get stops varying very much at all. And they become steadily, arbitrarily close to some limiting value. And that value, which they approach but might never reach, is what the expression is equal to. And nowhere along the way, no matter how big the maximum p gets, is that maximum p ever truly infinitely big. So there aren't any terms ever included in this product that would correspond to a non-terminating series of exponents. Until next time. So yeah, reasoning about infinity in math is just hard sometimes. But anyway, now that we have duly appreciated an Euler product, let's look at Sky's paper again. And it's at this point in the video series that everything that came before now begins to pay off. We're going to examine what's happening here. And I am going to be referencing almost every concept that I have touched on up until now. So the similarities to the Euler product that we just looked at are obvious, right? We have a sum to infinity with n to the s in the denominator. Sky has w of n in the numerator, and that's new. But remember, this statement that we're looking at in Sky's paper serves as a definition of w. So if we examine the right-hand side, we will find the usual product expressed over all prime numbers of an infinite sum, but it's been changed. And it's the changes on the right-hand side that serve to give us the definition of w of n. N has a prime factorization made up of terms p to the k. Now think about which terms on the right-hand side will correspond to a given n. Well, wherever k is 0, we'll be multiplying by 1. That much hasn't changed. And then when k is greater than 1, we have one of these terms. If we look below at the original Euler product, Sky's denominator, p to the ks, is the part that we've seen before. That much contributes to the n to the s that's in the denominator on the left-hand side, just like in the original Euler product. So what's new here? Well, two things are new. First, we have e to the I psi of p to the k. Like when k is 2, for instance, we have psi of p squared in the exponent there. And that's that psi function that we were talking about in the last video. Psi is going to be used to express an angle theta in the complex plane. But second, and very importantly, we have some alternating plus and minus signs. And in particular, we should notice that we have negative signs when k is odd and positive signs when k is even. And that should ring a bell if you remember our discussion of the Landau hypothesis, right? Okay, so what happens when we examine this for some value of n that has multiple prime factors? We combine a bunch of these terms to form one of the terms on the left. They're being multiplied together, right? Just like when we looked at the Euler product. As far as the pluses and the minus signs go, you should be able to convince yourself that it follows the expected rule. Two negatives multiply together to make a positive, just like two odd numbers add together to make an even number. A negative and a positive multiply to make a negative, just like an odd and an even sum to make an odd number, and so on. So, multiplying these pluses and minus signs together does correspond to adding up all the values of k. We will get either a negative or a positive result according to the number of prime factors being either even or odd, as desired. Then we're also combining these exponentiated terms. And of course, what happens when you multiply e to the a and e to the b? You get e to the a plus b, right? That's the principle. So we actually are adding these exponents up. Obviously, the p's and the k's are different here, but pardon my lack of subscripts for a moment. It's going to be in this form. The blue, came from one term. The green came from another term. We've added them up. And the imaginary number I can be divided out, and you get e to the I times the sum of the psi functions for each p to the k over whatever values of p to the k make up the prime factorization of n. Okay, as we know, the psi function is designed so that these sums range from 0 to pi. And pi radians is 180 degrees. So if the sine value turns out to be positive, then we have w of n as a point somewhere on the top half of the unit circle in the complex plane. If the sign is negative, well, a negative of a complex number, there's two ways to think of it. It's either the mirror image that we get if we reflect through the origin, or another way to think of it is the negative sign adds pi to the angle theta. Both of those will take you to the same place. Either way, we get w of n mapping integers with an odd number of prime factors onto the bottom half of the unit circle. So you're on either the top half or the bottom half based on whether the number of prime factors is even or odd. And now you know what w of n is. It's the function that takes an integer as an input and the output as a complex number on the unit circle. And it's positioned on either the top half or the bottom half, according to whether the number of prime factors is odd or even. And we also know that w is injective, which is a fancy word that means each integer n maps to a unique place on the unit circle. No two integers map to the same point. So on this little circle, we have a point for each and every positive integer, an infinity of counting numbers, rearranged to a new and mysterious pattern. Well, that's all for today, and I congratulate you for making it this far. In the next video, the next video is going to be shorter and easier to make, but I think it'll be uniquely rewarding in its own right. So look for video number 4 very soon.